Welcome, students and enthusiasts of data science. Today, we dive deep into the essentials of simple linear regression, its assumptions, and how to ensure your analysis stands up to scrutiny. So, buckle up as we uncover the secrets of SLR models.
Absolutely, Professor Whimsy. I'll join you in unraveling the intricate fabric of simple linear regression, or SLR, and we'll provide our audience with a robust understanding of why these underlying assumptions matter so much.
At its core, SLR is a statistical method that models the relationship between two variables. We've got our response variable, the one we're trying to predict, and the predictor variable, from which we base our predictions.
Yes, and the magic happens with the regression line, that line of best fit, which summarizes the trend of data points in our scatterplot. So let's march straight into the heart of SLR, the assumptions.
The first assumption is linearity, the cornerstone of SLR. Our model assumes a straight-line relationship between the predictor and the response.
To check for linearity, we can visually inspect this through a scatterplot. Do the points trend in a consistent direction around a straight line? That's our cue that the assumption may hold.
Then comes independence. Our observations should not influence each other. For example, one data point's value shouldn't depend on another's.
Correct, Professor. Methods like the Durbin-Watson test help us test for independence. Independence violations might indicate we need to reconsider our data collection process or model selection.
We then move to homoscedasticity. Ideally, the scatter of residuals should be uniform across all levels of the predictor. It ensures the variance is constant and your model isn't biased towards certain data values.
And if the variance fans out or in as we move along the predictor's values, we call this heteroscedasticity, right? Plotting residuals against fitted values helps us identify this.
Exactly. Last but not least is normality, the assumption that residuals, our estimation errors, are normally distributed. We can examine this with a QQ plot, or even employ statistical tests like Shapiro-Wilk.
Then we get to the real detective work, evaluating model assumptions with our trusty residuals. They can tell us so much about the health of our SLR model. They're the difference between observed and predicted values, and boy, do they speak volumes.
Through diagnostic plots, such as residual versus fitted values plots or scale location plots, we obtain visual cues to the validity of our model assumptions. Is the variance constant? Is the linearity assumption holding up? Residuals have the answers.
When assumptions fall short, fear not. There are powerful strategies to realign our model. For nonlinearity, we might transform variables using logarithms or polynomials, for instance.
And if we sense dependency amongst observations, time series models, or adding lag variables could be our rescue.
Heteroscedasticity might call for weighted least squares or variance stabilizing transformations. And for those non-normal residuals, sometimes a simple data transformation does the trick.
And let's not stay in the realm of theory. Real-world datasets bring these concepts to life. In our practical examples section, we'll assess and rectify these assumptions with real data.
It's essential to tackle the real data sets, because no amount of theory beats hands-on experience. You begin to see patterns and understand data behavior intimately.
So finally, we reflect on what we've learned. The assumptions of SLR are more than just academic checkboxes. They ensure that our predictions are reliable and meaningful.
Indeed, Professor Whimsy. It's our job as data scientists to do due diligence. This knowledge you've gained is powerful. Go forth, experiment, and let your analysis illuminate the world of data. Thank you for joining us on this journey through simple linear regression.